in this fourth set of the pre-lectures, we will start really looking at some really detailed features of object-oriented programming. So we're going to look at a feature called a class, which is really fundamental to what we're going to do in the rest of the course. So in order to tell what a class is, we really start from something called a structure, which is a rather logical and easy to understand, slightly more old-fashioned concept, all the way to what a class is. We look at the basic features of what a C++ class is. Specifically, we will discuss public and private data, access functions, constructors, destructors, member functions outside the class, and function return types. We then also try to discuss the relation between vector and object. Okay, so let's look a little bit at what we're doing. So, object-oriented programming is based on the concept of an object, which is almost a tautology. But what is an object? In order to understand what an object is, you really need to think of a real object. An apple, a pencil, a car, which are defined by their properties, which are usually expressed in nouns, but they are also defined by their functionality, stuff we express in verbs. And you can actually extend this concept to how we store and manipulate data, and people have found it beneficial. A simple way to capture all the properties, so not the functionality, is a struct. And the struct actually originates in the C language, so it's a slightly older way of doing it, even though it's been taken on by the C++ language. I'll discuss a little bit later what the minor differences are. Think about a particle, the way we would describe a fundamental particle in particle physics. You could define a struct to hold its properties. And in that case, the properties might, so a struct is called struct particle. You open a curly bracket, close a curly bracket, and in between you say string type. So that string stores the type of particle, and we would have three double variables which store mass, momentum, and energy, for example. Okay, but this is quite a good start if you want to do its properties. Now, in that case, once you've declared a struct is actually like a type. It's like a string. You can deal with it in almost the same way. And what we can declare two particles, one called P1, the other called P2. And then we can set the value for the two particles. P1, the type would be electron, and its mass would be 5.11 times 10 to the 5, so mass expressed in electron volt. We should have said what the units are, of course. We didn't. And the momentum could be a million electron volt over C, and then we could calculate its energy by just calculating the square root of the square of the mass plus the square of the momentum. And for a proton, it would be slightly different. It would be 938 times 10 to the 9th, so giga electron volt. And its momentum, for example, could be 3 giga electron volt over C. And once again, we can calculate its energy in exactly the way we expect. So there's no big surprise there. Now, once you've done that, you want to do something with that. So you could write some functions to print, for example, want to print out the data, which takes a construct as an argument and then prints out all its properties with a certain precision, which really means two significant figures. And then it could do this neatly by putting some square brackets around it, putting types, putting some commas in between, etc., etc. Or we could calculate the Lorentz factor, the thing we usually call gamma, and that would just essentially calculate the energy over mass. And if you think carefully, that is clearly the way to do it. So if I were to write all of that in one code, this just combines everything in there. Remind you that we use both the string header file as well as the CMath header file. CMath contains actually the square root operation, which is one we're going to need to define the energy, if you remember carefully what we did before. So you've seen the struct before, you've seen the print data before, you've seen the gamma before, you see exactly how I create the particles, how I define the properties of the two particles, and then essentially it's all done, and then I can print the data, and I can also calculate the Lorentz vectors if I want to do it. Now this is a slightly awkward way of doing things, so let me explain to you why this is nice, but not as nice as it should be. So I call that structures why not. I mean, if the program runs, it runs and it does perfectly well. But there are some disadvantages to this method. The data that's contained in each struct must be defined outside of the structure declaration itself. And that has various weaknesses. It makes it very easy to forget to set a value. For example, to forget to calculate the energy. So the data is open to being altered or corrupted because I can access it in any part of the program and I could do something stupid. Functions acting on the data, so those were my verbs, are separate and require the data to be passed as a parameter. Neither of those are totally attractive and actually make codes much more error prone, and errors are the bane of every programmer's life. So what if we could combine the data and their functions in one structure? And that's really the key of object-oriented programming. And this is exactly what C++ offers in the form of what is called a class. So let's turn our struct into a class. And the first thing I'm doing it in the most stupid class, which does exactly the same thing as our struct already did. So we declare a class particle, and inside the, it says struct before over there, it looks almost exactly the same. The only thing that's different is that we added the keyword public over there, and we need to work out what the keyword public really means. So the code, as part of a code, it would work completely identically as the struct did. And the reason for that, the C++ definition is a struct is a special type of class where all members are public. So no big surprise, if we have a class where everything is public, it's equal to a struct. And in our main function, as I'll show you in a minute, now two objects are created of the class particle and their instance of the class. But the public keyword is really the important one. This instructs the compiler that everything declared below it, so this everything over here, can be accessed from outside the class. So all of this data is available for any function anywhere in your code. Anything not declared public, so not explicitly made public, will be invisible outside the class. And that's usually called it's private. There will be a third option, which we'll see in later weeks, which is called protected. So the three P's, public, private, or protected, they're all P words, and that's exactly how it works. Okay, so if we were to change our class by just changing one line, I turn the public into a private, which means the data is now private to the class, and if you compile that code, so that would be class 2a, you get a very large number of errors, as we are accessing private members outside the class. So we can't do it. That looks like a problem, but it isn't. It's actually an advantage, because it allows us to keep data secure, but we will need to define a way to access this private data in a safe and secure and controlled way. And that's all this is about. So, apart from the public nature of the data, the main distinction between a class and a struct is that the class can, and almost always will, include functions to manipulate its data. So, let us define one to set our type, and one to print its value. So this is the first stage we do. So this is based on the class where everything is private, but we've got a set of public functions. One of them would set the type of the particle by taking an input string and then assigning that the value of that input string to the type I have over there. And another function that prints out the type of a particle, and it does exactly what it says on the tin, so essentially it prints the type of the particle. So these two public functions are there because we wish to access these functions from outside the class. So the methods of the class are available outside the class, but its data not. When a new object is created, we use the functions to refer to the particular object. We access these functions in a similar way to accessing the object's public data. So you write my object dot my function of my argument. So that's the way you call a class function. It says my object, which is of a certain class, and then it calls the function on my object. So that makes it clear that the function is associated with the object. And a simple example would be particle p1, p1.setType type, p1.printType, and you can clearly see what we do over there. Now, the best way to access the data is through access functions. And for example, p1.printType is an in-between. It's almost an access function. We can protect our data from any undesirable consequences by designing these access functions to suit our data and the way we want to manipulate our data. So that you can do some quite smart things this way. But still, setting all the variables by access functions becomes rather clumsy. And if it gets too clumsy, usually somebody comes up with a better way. And there are two special functions called the constructor and destructor. They can be defined. If you don't define them, then the compiler will always generate a default constructor and a default destructor. So essentially, if you have anything special you want to do, you better define it yourself. A constructor is that function that is automatically called when a new object is created. So when we declare it. It can be overloaded to give different actions depending on the arguments. So essentially, well, we'll see an example of it in a minute. It has the same name as the class itself and has no return type. Its main use is to set the values of the object's member data. It could have some other effects as well, but the notation we'll use will make that abundantly clear. And similarly, a destructor function is used to destroy an object's member data. It typically is called at the moment at any point where the data will no longer be available to a code. And we'll see examples of that as well. So if we do that for our class, and so we still got the same story. We've got our private elements, and now we declare a default constructor, which actually declares the particle of type ghost, mass 0, momentum 0, energy 0, and it has no function body. This type of declaration, where we actually put a colon and then the initializations over there, is actually the preferred notations. If you grab an older book, they may not yet do it that way, but these days it's often the preferred notation because it says that any side effect my code has, anything beyond initialization, goes in the final square curly brackets, but essentially just setting these values goes over here. Now we declare two constructors. The second one is called a parameterized constructor, which actually takes 1, 2, 3 arguments and then sets the type based on the input type, sets the mass based on the input mass, the momentum on the input momentum, and automatically calculates the energy based on the mass and momentum. So that's quite a neat way of doing it. And then we also declare a destructor, which I should probably have made slightly clearer that it happens over here. So we set destroying, and it just outputs that. It doesn't do anything in this case. Destructors will become more important if we actually allocate all kinds of weird and wonderful data sizes, which we'll see later. We've got a function gamma inside here that returns the energy of a mass, and we declare a function print data. So let's look at the first constructor, the default constructor. Essentially, it will be called when we declare an object with no parameters. If you say particle p1, so then these variables are initialized in that way. The particle type is ghost and all the other data are set to 0. The destructor is typically called when a function exits. So including main. So if you declare particle in main, then this will be called, and so you can test out what happens with the code. You just run the code and you see it gets destroyed. It destroys quite a few particles. But a destructor, an explicit destructor, is really only useful or really important when you have dynamically allocated memory. Because if you use new in the constructor, delete of the data would go over here. It's always good practice to include a destructor just so you make sure that you don't forget it and you know exactly what action it takes. So also I said we had this parameterized constructor as well, which allows us to pass data when creating an object. It also computes the energy, which is clearly a useful thing to do. So we don't have to do it ourselves. So far, all the functions were defined in the class itself, but we have not specified the details for print data. Print data is what we call a slightly larger member function. It's a bit of an artificial argument, but some member functions are very, very large. So if you give all the detail of what a member function looks like inside the class definition itself becomes unreadable, and it makes the code look clumsy. So the solution is often put the implementation of a member function outside of the class, or even in a separate file, something I'll discuss later on in the course. The important note is that even though you can actually define the implementation of the function outside the class, you still need to give the prototype of the function inside the class. So it's just like a forward declaration you've seen before. So the example I've used over here was the function that prints an object data. You first declare its existence inside the class using the function prototype by saying void print data, and then outside the class you need to define the function itself. Notice over there that the declaration gets prefixed by the particle : and the : is called the scope resolution operator. If I didn't do that, then this function would not be the class function I'm defining, and it would not have access to private member functions. Since this is a function inside the class, this function will have access to type, mass, momentum, and energy, so I can do it that way. So if I did not put this stuff in there, the compiler would actually believe the function to be an ordinary function, not a member function of particle, and then it cannot access private members. So you would get an error message from the compiler, which is not something you want. Our member functions have not returned anything up to now, but it is possible, as it is a normal function. And as a good example of that, if you define the function that determines the Lorentz function gamma, which I did over there as double gamma return energy over mass, then clearly I've got a function that does that. And the way I would call it, I would call p1.gamma, and I can probably output the data that way. So I get a very elegant way to do exactly what I wanted to do before by calling the class function on that. Now, there's a final refinement. Suppose I have lots of particles, and for example I look at a certain collisions where there's lots of particles coming out, and I want to store all the data of all the particles I've seen. Now I'll do that for 2 particles because I don't want to do it for 100 particles, but in principle there's many more. So what I could have declared was a vector of particle data. So that's quite a useful one. And then I can actually push back, add to that empty vector I've defined over there, a particle defined like that over here, and I can also push back the second particle would be the proton, and then I can print out the details. The easiest way is using an iterator. So rather than explicitly declaring the iterator in this rather cumbersome way over here, I use the auto declaration over there to actually see what happens. I define p current, which is the begin, it goes less than the end, increment it, and I do one more weird thing. I do this thing, which is a combined dereference, so a star, and a dot, which is usually written as this arrow function. So this is the member of the object picker is pointing to. Remember that an iterator is very similar to a pointer, and that helps us, and we can do the same thing over there. So this is a new notation just to make it slightly easier, because what it really means is the same as bracket star picker dot print data, and you can clearly see it's much easier to write an arrow than that. And it's just remembering that an iterator is essentially a pointer. Okay, let's recap. A class is the set of rules used to define our objects. It specifies which types of data and functions are created and their scope, their accessibility, whether they're private or public. An object, for example the particle P1, is an instance of a class. Each object will have its own copy, its own set of data. A member refers to either data or a function belonging to a particular class. A constructor will be a member function. Member functions are also sometimes called methods. A constructor is a special function called when a class is instantiated, usually to initialize an object's memory data. It's not if the user doesn't explicitly declare it, the compiler will create one for you. A destructor is the function called when an object is destroyed, and usually automatically when exiting a function. We say the object goes out of scope. This happens when we can no longer access the object. And again, if the user doesn't generate a destructor, the compiler will do it for you.